Hey guys, welcome to a new video in this computer vision tutorial. In this video we're going to talk about corner detection first of all we're going through some of the basic stuff about like what corner detection is, how we can do corner detection, and then we're going to talk about some of the algorithms that we can apply to detect corners in the image. But first of all, remember to hit the subscribe button and also like the video to help me and the YouTube channel to grow even further. And I'm just really thankful and I really appreciate your huge support. It really helps me out building this channel. So let's jump into the video here, where first of all we're going to talk about corners in images. So what is actually corners in images? So we're talking about like features in images where we're going to like extract and detect features, kind of features and information in images. So when we're talking about features in images, they are matching points between the frames of an environment. So we can say that if we, for example, take like two different kind of images and we try to like match some of those points between two frames of an environment, then we can have a feature between those 2 points in the two frames. And we can relate images to each other and extract information from 2 images and compare like some of the frames, some of the pixels from one frame to the other frame. And then we're matching the points. They are like characteristics that we can recognize easily. This is what we call features when we're trying to like recognize something in one frame to another frame. And features are uniquely recognizable. So if we extract some information from one image, like they're unique to that point, and we should try to like recognize that in the other image, which is also like unique. So that's why like features are uniquely recognizable. And we have different types of features in images where we have edges, which we talked about in the last video, where we talked about like how we can detect edges and how some of the algorithms works for edge detection in OpenCV and also just in computer vision in general. And then now in this video we're talking about corners and how we can detect corners in images by extracting some information and doing some different kind of stuff. So these are like the interest points. Like corners in an image is like the interest points where we can extract, like for example, a frame around a square or something like that. So it is really like what like it's really like just the interest point of an image, and we can do a lot of different kind of stuff with corner detections and extracting information and doing object detection and stuff like that. And then we can also have blobs, which is also a type of feature, which is just regions of interest instead of just one pixel or one specific point, which corner. So a corner is an intersection of 2 edges. So in the last video we had edge detection, and then when we're detecting 2 edges and they intersect on each other, then there is a corner in the intersection. So the point in which the direction of the 2 edges change is an intersection, and thereby a corner as well. And we're detecting the intersections here where the gradients for the two edges have a high variation, and then we can detect corners in that way. So this is more like just the basic stuff and some of the like the background knowledge of what corners is in images. And then now we're going to talk about how it works and how we can extract information and detect corners in images with different kind of algorithms and methods. So first of all, let's talk about like how we can find corners in actual like images, where first of all we have to determine the correctness values for each pixel. So we go like through all the pixels in our image and we find the main differences between the approaches, and then we can produce a cornerness map. So we try to like find the corners in our image by going through all the pixels, like each pixel. And then we use the non-maxima suppression, as we talked about in one of the previous videos on edge detection. So we use this non-maxima suppression when we're like extracting information or like finding features in our images. So we have like multiple responses here in the non-maxima suppression, which is the image over here, when we're doing this non-maxima suppression on our like cornerness values. And then we can compare like these values over here to the local neighbors, and then we can detect edges in that way. So when we have these non-maxima suppression where we can compare them to local neighbors, we can apply this threshold here to the cornerness map. And we apply this threshold here by setting up like a threshold value, and if they're over that value, like we will accept it as a corner, and if it's under that threshold, we will reject it as a corner. So by using this threshold here on the corners map, we get the most significant corners, as we can see over here. Like we don't detect every corner in our image here after the non-maximum suppression, but like we can see here, there's a lot of white up here and also like some of the corners here. So these are like the most significant corners in the image, and that's why we only detect like some of these corners here with the arrow and at this sign here, and also like the sign up here, and some of the text here as well, because this is the most significant corners in this image here, and not really like over here which we can also see on this non-maximum suppression image. So if we're actually going to apply this corner detection in some way in OpenCV and in computer vision, we can deal with the Harris corner detector, which is an implementation of like how we can find corners in an image. So to find corners in an image with this Harris detector here, like the approach is to find the variation of the intensity in the image. So we can set up this equation here where we have like the variation of the intensity here to the left. And then we have here, which is the window at position. So we're dealing with windows here where we're going over the image in windows. And then we have like the intensity at the move window here. So when we're moving the window, we have this intensity here at the move window. And then we have like a displacement here in the X direction, and also a displacement here in the Y direction, which is the U and V here. And then we subtract that here with the intensity at the pixel coordinate. So this is specific pixel coordinates that we're looking at. And then we have like a window that we're going over and trying to detect the corners. So this is just like the mathematical formula for this variation of intensity, and then we can like put this by using on matrix form. By using, first of all, we can use something called a Taylor expansion, and then we can rearrange some of the terms, and then we can put it on matrix form. And when we put this in, when we do this to this equation up here, we'll end up with this equation down here where we have this m here, which is equal to this window here at some pixel position. And then we get this matrix over here, which is just like what is here, but on matrix form when we have used the Taylor expansion and rearranged some of the terms. Like it's not really that important. It's just like this is just a way to set up mathematical and how we can implement it in code. And then over here to the right here is like when we're trying to estimate this variation of intensity here. Then we have this UV vector here, and then we have this m here, which is this like sum of the matrices over here, and then we have the UV here again as a vector, and then this is actually like the variation of intensity that we're going to apply to find our Harris or our corner detection by using this Harris method. And then when we have done this here, and we have the variation of the intensity, then we can calculate a score of the probability that it is in a corner, and we can then make sure like we get the corners that we're most certain that are actually corners. Then we calculate the score here, which is the R here, and then we have the determinant of the M matrix up here, and then we have this K trace M here, which we can see down here that this determinant of M here is some of the eigenvalues that we're going to talk about later in this video as well, where we just multiply these two eigenvalues, and then the trace M here is just when we sum these two eigenvalues here. So a window with the score R greater than a certain value is considered a corner. So this is the threshold that we're talking about. So if R is greater than some threshold that we set up, then we accept that pixel as a corner in the image, and if it's under that, we just reject it and it is not a corner in the image. So this is a way we can set up like a score of the probability that we think that this is the corner in the image, and then we can play around and tune this parameter and this threshold value. So we'll see when we apply the Harris corner detector here in code and OpenCV. So first of all, here we have this grayscale image that we're going to apply this non-maximum suppression on. And then we can see that we get these white pixel values here, which is the local maximums in the image. And then when we actually like apply the Harris corner detector, we can see that these white points here actually like are corners in the image. So we can see that we detect some of the corners here and a lot of different kind of places here in the image. So this is like a kind of a good result for this Harris corner detector, but we can see that we skipped like some of the corners here in the image, but we could tune that with some of the parameters, and we want like when we're doing this many corner detections here in an image, like we will get a lot of false positive, and we will also like miss a lot of different kind of edges. But we can choose different kind of parameters, and we can also try out other corner detections, or like make one ourselves that fits to our application. So another method here that we're going to talk about is the Shi-Tomasi corner detection, which uses eigenvalues to detect corners, and kind of like the same approach as the Harry corner detector. So it calculates the corner quality at every pixel in the image. So we go through all the image pixels, and then we calculate the corner quality, and we say like how good is this pixel, and could it be a corner, and how good is the quality of this corner here that we found. And then we're again going to apply this non-maximum suppression here, which we're going to apply in all of the methods when we're doing corner detection. And then we find the corners with the minimal eigenvalues less than some threshold, which then get rejected if they're less than the threshold, also as the same approach as the Harry's corner detector. And then the remaining corners are sorted by quality in descending order, and then we can like take the best corners. So we throw away all the corners where it is a better corner at a distance less than a maximum distance. So we set up some threshold value for distance as well, so we don't detect corners that are like really close to each other, because they have like if they're better corners at a distance less than the maximum distance, then they will just take that corner instead, and then we can extract better, and we won't get that many like detections of corners in an image, and also like false positives. So this could be like an approach to make this corner detector here better, where we get some false positives around like here, and also like a lot of different kind of other places like up here. So that could like be one way to fix that problem, but there could be like specific different kind of problem for each application. So we need to like try different kind of corner detectors, and also play around and tune some of the parameters that these functions take in OpenCV. So here's the result of this Shi-Tomasi corner detection, where we can like have the maximum corners, like we give it the maximum corners that we want to detect an image, and we can see down that here that we don't detect that many corners as with the Harry's corner detector, but we can see that we get the most significant corners here in the image, because we applied this maximum distance here. So if you, for example, detected a corner like here, then it will probably not be seen as a corner, because we had this corner here, and the distance here is not over the max distance threshold that we set up. So then it will not be a better point here than compared to here, because it is not close enough. It is too close to each other to be a point, or like to be 2 points. So we can see down that here that we get like these different kind of points here, which describes like the textures, or like the squares and triangles here better, by using like a less corners, but the corners that we're actually like detecting, we're very certain that these are corners, and also that the quality of these corners are really high, because we take the highest the corners with the highest quality, and also if they're corners like close to each other, then we don't care about those, and we only take the corner with the highest quality. So another one here that we can do to like get some more exact corner positions is to do corner detection in the subpixels. So an example here is that we can like find the subpixels in an image. So a way to find more exact corner positions by using subpixels. So the image here to the left is the subpixels of an image, and then we can see down that here like we get a really exact position of the actual like corner that we're detecting in this image here, compared to the right over here, where we just have like, okay, here is a corner, so we detect something here, we just put a circle around here, but this is not really exact, because over here we're using pixel integers, but over here we use these subpixels here, so we get a more exact position of where this position of the corner actually is. So we can see that here, like if we only use this integer, like this will be like the range of where this corner could be, but now we get a more exact position of it here, because we're using these subpixels, and we get like these transitions here, or like the intersection of our edges, which is corners. So this is a way to like get a more exact corner detection algorithm, but it will also like be a bit more computational time, and it will like and it will slow down a bit. But if you need like the precision and having the exact position of the corners detected, like you can use this this approach here where you're detecting the corners in subpixels. If you have some different kind of applications and the built-in functions, or like the Harris corner detection, or the other one is not good enough for your application, you can also create your own by using the same approach as the Harris and the Shi-Tomasi corner detector. So you can create your own by just finding the eigenvalues and eigenvectors to determine if a pixel is a corner, and then we can use these eigenvalues to find like the minimum eigenvalues, and then those eigenvalues will be the corners in our image that we have detected, and then we can have a bit more freedom with some of the parameters in the algorithms here to make a specific edge detector for our application, and then tune the parameters for our application. So if you have some specific application that you want to do this edge detection on, it will probably be a bit better to create your own and take the same approach as this Harry and Shi-Tomasi, just to get a bit more freedom. But if these are built in up here, works fine. Just go use those. They're debugged a lot, and they're also actually really good, and you can tune the parameters and see if you can fit those to your application. So let's jump into code here and see some different kind of examples on how we can actually implement corner detection in OpenCV and C++. So we're now jumping into Visual Studio here, and I'm going to show you some different kind of examples on the Harris corner detector, and also the other one that we talked about, the Shi-Tomasi corner detector. So first of all, let's go with the Harris corner detector here and see how we can implement this in code. So first of all, we just have some images here, or some matrices where we're going to store the images on when we're doing our operations on the images. And then we're going to load in an image here that we're going to apply the Harris corner detector on. First of all, we just check if we could load in the image, and if not, we just throw out an error loading the image. And then we show the original image, and then we converted the image to a grayscale image, because when we're doing the operations and the non-maximum suppression, we're first going to grayscale our image. And then we're going to apply the actual built-in function for corner detection with this corner Harris built-in function. And this is used to detect the corners in the image. So first of all, it takes the input image here, which is the grayscale image, and the output image here, which we already allocated zeros to here. So we're just allocating space here to the output image. And then we have some neighborhood size here, some parameters that we can tune on if we want some different kind of detection of the corners and stuff like that. So if it doesn't fit for your application, you can tune some of the parameters here and get a better edge detector, or corner detector. And then we also have this aperture parameter for the Subpixels operator, and we talked about the Subpixels operator in the previous video when we talked about edge detection. And then we have this Harris detector free parameter here, which you can just play around with and tune to get the most optimal corner detector for our application. Then we're going to normalize our image here first of all, and then we're going to convert it, so we can convert it to values to integers, so they can be drawn on our original image. And then here we have these two follow-up here, which is just going to draw the actual circles around the corners that we have detected with this Harris corner detector up here. And then in the end here, we're going to resize the image so we can see what's going on and what the result is. And then we're going to show the image of the edge detection that we have applied and drawn our circles on. So if we go down here to the main loop here, let's first of all let's get the Harris corner detector here. And if we run the program here, it will just run the program here, and then it will show up the image here of the edge detection. And we can see that here to the left we have the original image here of this house here, and then the output of our Harris edge detector over here. So we can see that we have actually detected a lot of edges up here, and some of them really close to each other. So we could actually use the other method with the distance, so we don't really detect all of the corners here close to each other. And we also have a lot of corners and false positives over here in the tree, but we can see that here at the chair we get some good detections, and also here in the windows and stuff like that. So if you want a better edge detector or something like that, we can play around with some of these parameters here. That's the wrong one. So we go up here again to the Harris one here, and we say 0.02, and then we run the program again. We can see that it has changed the edge detection, and we can see that we don't detect that many edges now. So we can play around with these parameters and see what works best for our application. So the other example here is the Shi-Tomasi Corner Detector here. So first of all, we're just going to do the same as with the Harris Corner Detector, where we're going to have these images up here, and then we're going to read in the image. We check if the image could not load, and then we convert it to a grayscale image. Then we can use this function here, good features to track, which is the built-in function for this Shi-Tomasi Corner Detector, and then we store the result in this vector here up here with points of floating points. So we have 2 here because we have x and y for our corners that we're going to detect in the image. And then we have some different kind of parameters here again, where the first one here is the max corners that we want to detect. So in this case here, the maximum number of corners that we want to detect is 100. Like we can maybe like put it down to 50. And then we have this minimal quality of corners. So if the quality is under this threshold value here, we'll just reject the corner. And then we have this minimal Euclidean distance between the return corners. So this is like how far away the corners are. And then we choose the corner with the highest quality, and then we choose that. And if there's any corners detected close to each other, like that, those will just be rejected. Then we have like an optional region of interest if we want to like find these blobs in images with the features as well, instead of only finding the corners. And then we have the size of the array block for computing a derivative covariance matrix for each pixel in the neighborhood. And then we can also have some different kind of like, if we want to use the Harris detector approach, or the corner where we to like find the minimum eigenvalue of the corners, and then use that approach as well. In this case here, we're going to apply this corner min eigenvalue function. And then we again have some free parameters here that we can tune if we're using the Harris corner detector. And then we're just going to like draw the circles that we have detected, or like the corners that we detected in the image, and then we just show the image down here again. So if I run both of these here, both of these edge detectors here, like we see the different kind of approaches. And the first one here is that we detect this output here of the Harris edge detector. And if I hit control here, we can see that now we have applied this Shi-Tomasi edge detector here. And if we just put them up here side by side, we can see that there are some different kind of differences. Like here, we can see that we don't get all of these close edges here, like corners detected here close to each other, because we're using this this distance here between corners, and then we just choose the corner with the highest quality. And we can see that here, like we detect a lot of good edges here at the roof, and also like some of the windows and chair here. And we don't get that many false positives as over here, and we don't detect that many corners close to each other because we're using this approach here instead. But we still get a lot of like different kind of edges detected, or like corners detected over here in the trees. So we can see that this Shi-Tomasi approach here is better for this application here compared to the Harris edge detector over here. But the Harris edge detector could be better for some other different kind of approaches. I also have another image here that I can show you how it works, but it's just squares, and then we're detecting edges, or like no corners in the squares of the image. So if we just run the program here again, we can see that we're just detecting the edges here, and we can see that in this case here, the output Harris actually like works better than this Shi-Tomasi here. Like some of these edges up here is not detected, which is in the output Harris detector over here. So in this approach here, like the Harris edge detector is better, but we could maybe detect some of the corners here if we try to like play around with some of the parameters in this Shi-Tomasi edge detector here again. So it's all about like trial and error and setting up these edge detectors and using the built-in functions. And if they don't fit for your application, like you can just go create your own, find the eigenvalues, and then take the minimum eigenvalues, which is the corners in images, and then you can apply that for your application. So that's it for this video, guys. Remember to hit the subscribe button and bell notification on the video, and also like this video if you like the content and you want more in the future. I'm currently also doing an artificial intelligence tutorial where we are now talking about reinforcement learning and how we can deploy an agent and have it learning by interacting with the environment, and then do different kind of stuff. And I'm also doing an algorithm data structure tutorial in C++. So if you're interested in one of those, I'll link to one of them up here, or else I'll just see you in the next video, guys. Bye for now.